In this video, I'm going to talk about the two coils example, which was in Handout 22, problem number 3. It's also on page 910 of the textbook. So in this problem, we have two coils. This coil has a current in it called I1, and I1 changes with time. Therefore, the magnetic field due to coil 1 changes. So coil 1 is creating a magnetic field that's changing. And since that magnetic field is changing, then over here, there's a changing magnetic flux through coil 2, which in turn causes an EMF in coil 2. And so our goal is to find the EMF in coil 2. Okay, our first job is to come up with a formula for the magnetic flux in this coil right here. Okay, and here it's given to us the strength of the magnetic field due to coil 1, right? That's why the subscript 1 is there. This is the magnetic field due to coil 1, and this is telling us the strength of that magnetic field over here where coil 2 is. And in this case, Z is the distance between the coils. I1 is the current in coil 1. We would expect B1 to be proportional to I1, right? More current, more magnetic field produced by the coil. And here pi r1 squared, that's the area of coil 1. R1 is the radius of coil 1, and here we have N1, that's the number of turns in coil 1. Okay, so let's find the magnetic flux through coil 2. So we'll start with the definition of magnetic flux. Let me put a 2 on here to make it clear I'm talking about coil 2. And this is equal to the integral of B dot n hat. Okay, so this is the amount of magnetic field, if you like, or the number of magnetic field lines penetrating the area in coil 2. Okay, so this B is the B that's produced by coil 1. So this is B1. N hat is the normal to coil 2. Okay, which is drawn here and here. And then dA. And we're taking this integral over an area. Which area? Well, we're computing the flux through coil 2. Therefore, we're taking the integral over the area of coil 2. So this is over coil 2. All right, let's look at this B1 dot n hat term real quick. So that's a dot product. So that's going to be equal to the magnitude of B1 times the magnitude of n hat times the cosine of the angle between them. And here we can see that the angle between n hat and B, because B is horizontal here, and n hat is at an angle, the angle between them is 35 degrees. So this is going to be the cosine of 35. The length of n hat is just 1. Okay, so I'm going to plug that in over here. And so I'm taking the integral over coil 2's area of B1, just the magnitude this time, times the cosine of 35 times dA. And now, if we look here, there's this important assumption here that we're assuming the magnetic field B1 is the same across all of coil 2, which when you look at this, you can see that's not going to be exactly true, because the part of this coil, since it's at a tilt, the part of this coil that's farther away from coil 1 is going to experience a weaker magnetic field than the part that's closer. But we're assuming that this distance is large enough that this little bit of tilt doesn't really matter, okay? And so we're going to assume then that B1 is constant everywhere in coil 2. So that is the magnetic field due to coil 1 is constant everywhere in coil 2. And so since this is a constant, I can pull it out of the integral. Cosine 35 is just a number. I'll pull that out of the integral. And what I'm left with is the integral of dA over coil 2. Well, the integral of a lot of small areas over the entire area of coil 2 is just going to give me the area of coil 2. So this is B1 cosine 35, and the area of coil 2 is pi r2 squared. Now we have the formula for B1. All right, so I'm going to plug that formula in right here, and we're going to get a big equation out of this. So we'll have N1. Okay, so here it is. notice that we have the area of each coil is now appearing in the formula for the flux. Okay, so now we're ready to go on to the next step. Now that we know the flux, we're ready to take the time derivative of the flux in order to find out the EMF. So looking at this, which of these things is changing with time? Well, the coil radii are not changing with time. We're assuming the coils are not changing in size. Z is not changing. We're assuming that the distance between the coils isn't changing. These are constants, so obviously they're not changing. We're not adding or removing any coils from the first coil. All right, so the only thing in this equation that's changing is I1. So with respect to time, that is. The only thing changing with respect to time is I1. So I can, when I take the time derivative of this big thing here, all of this is a constant that I can pull out. And I1 is the only thing that's going to be left inside the time derivative. So let me write that out. Okay, so here I have the absolute value of the EMF is equal to the absolute value of the time derivative of the magnetic flux, which is this formula that we found here in part A. All right, so now I'm going to do what I was saying before. All of these things are constant in time. None of them are changing with respect to time, except for I1. So all of this is going to come out of the derivative. Okay, and there we go. Now, this is an EMF in coil 2, the EMF induced in coil 2, assuming that it's just a single loop. Now, if coil 2, it actually has 1,500 loops, right? So what is the flux through, or I'm sorry, the induced EMF for, if this is one loop, what is the induced EMF for 1,500 loops? Well, I need to multiply this quantity by N2 as well, okay? So EMF is going to equal N1 times N2 times all the rest. Okay, so this is an interesting formula. Look, it's got both N1 and N2 in it. It has R1 and R2 in it. So clearly the geometry of the coils, of both coils, is very important in determining what the final EMF is going to be in coil 2. Okay, now we have numbers to plug in here, but we need to figure out what this is. So what we're going to do here is we're going to approximate it with an average. So we know that this is an instantaneous change, rate of change, but we can approximate that with an average rate of change. And these are numbers that we're given. So looking back up here, let's see everything that we're given. So they're 20 centimeters apart, so that's Z. Coil 1 has a radius of 8 centimeters and 3,000 loops of wire, so that's R1, N1. Current I1 is varied. Coil 2 contains 1,500 loops, so that's N2, and a radius of 5 centimeters, so that's R2. 35 degrees is already in our formula. Oh, and I just realized that I probably dropped that cosine 35 at some point, so I'll go and fix that. And then here is the current changes from 0 to 3. Okay, so now that gives us delta I1, and it happens in 4 milliseconds. So delta I1 goes from 0 to 3, so that's a change of 3 amps in 4 milliseconds. I'm going to convert that to seconds, so that's 0.004 seconds. Okay, and now the cosine 35, I dropped it up here. So I plugged in for B1, I included the pi R2 squared, I forgot to include the cosine 35. So this is going to be times cosine 35, and then I'm going to need the times cosine 35 in here, and times cosine 35 right here too. Okay, and so let me get rid of this, cosine 35. Okay, so we have all these numbers. Let's plug them in and see what we get. All right, so we end up with this formula when all the numbers are plugged in, and I put that into a calculator and ended up with 10.9 volts.